So for this video, we're going to look further into displacement time graphs and how they work. We looked a bit into them, but not too deeply. Let's try to look a little bit more deeply into them. So we've got the first one. Displacement is always on the y-axis and time on the x-axis. So the gradient shows the speed or the velocity of this graph, because gradient, we can basically get that by doing the y-axis divided by the x-axis, which is the units for speed and velocity. So let's try to interpret a few examples, the commonest examples of what we'll have on a displacement time graph. So the first one will be a straight line. How could we form a straight line? Well, we have an object right there, and let's say that in 5 seconds it covers a distance of 5 meters, right? Okay, 50 meters. Then at 10 seconds it goes all the way to 100. So in the first 5 seconds, how much distance did it cover? Covered all the way up to 50. Then from 5 to 10 seconds, it went from 50 to 100. So from 5 to 10 seconds, it covered how much? Another 50 meters. Then what about from 10 to 15? Let's say it covers another 50 and goes up to 150. So from 10 to 15, it covers another 50 meters. 50 meters. I think you can see the trend. And then from 15 to 20, let's look at this. From 15 to 20, it covers another 50 meters. So it goes from 150 to 200, something like 200. Not properly accurate, but I guess you can see what you mean. So you can see that every 5 seconds, it's covering 50 meters. Every 5 seconds, it's covering 50 meters. Every 5 seconds, it covers 50 meters. So when you try to get the speed, we'll say 50 meters divided by 5 seconds. The distance covered divided by the speed to give us 10 meters per second. So when we have a straight line like that, that shows us that we have a constant speed, because every 5 seconds we go up by the same amount. Another 5 seconds, the speed, the distance covered increases by the same amount. Another 5 seconds, same amount of distance covered. Another 5 seconds, same amount of distance covered. So for each unit of time, the distance we cover is the same. So that means that the speed is going to be constant right there. So in a displacement time graph, a straight line shows constant speed. Now you can have different types of straight lines on this graph. Let's see what are the different types of straight lines you can have here. Let's look at those. So you can have a straight line that's slanting in that direction, but you could also have a straight line that's slanting in maybe a direction like this. Let's try to interpret what it could be. Well, here at this point, maybe let's take it as 1,500 meters. Remember, displacement measures how far away you are from a point. So if you're at 0, maybe that could mean that you're at home. And if you're at 15,000, that means you're 15,000 whole meters away from home. Right? So let's see what happens next. So this time, as the time passes, we have time passing, maybe 10 seconds. It looks like the person is now 1,200 meters away from home. Yeah, just an estimation. Then maybe at 20 seconds, they're now how many meters away from home? They now say 1,000 meters from home. So like, it seems that they're getting closer and closer to home. At first they were 1,500, then they were 1,200. Now they're 1,000 meters from home. Soon they'll be 500 meters from home. Soon they'll be 100 meters from home, maybe somewhere there. They'll be 100 meters from home, then 50 meters from home. Then finally, when they reach 0 meters from home, that means they're actually at home. So it seems like they're going from, they're far away from home, and then they're approaching closer and closer and closer. They're getting closer and closer and closer to home. So if a line is starting from 0 time or any time, but it starts from a high displacement and then gets lower and lower, goes to 0, that just means that the person is just approaching the home. It's traveling in the backward direction, and that means they're traveling backwards. These are all straight lines though. We're going to soon look at what could a curved line mean on something like this. Let's look at that. Okay, let's get these dots off. There we go. We talked already about what a straight line could mean, something like that. Say this is 200 meters. So you're 200 meters away from home. 5 seconds, you're 200 meters away from home. 10 seconds, you're still 200 meters away from home. 20 seconds, you're still 200 meters away from home. 40 seconds, you're still 200 meters away from home. What could that possibly mean? You're probably taking a break, you're probably resting, you're probably seated somewhere, or you're not moving. What's the gradient of a line that's horizontal like this? The gradient is 0. So in the same way, because the displacement is saying the same, we're going to say the velocity here is also just 0. They're not moving. Now let's look at some curved lines. How could we get a curved line from a displacement time graph? Let's see. So let's say that in the first second at time 0, you're right at home. So you're right there. Let's use maybe a different color. Let's use a blue. So at time 0, you're right there, just at home. Let's see, let's get in a blue, a proper blue. There we go. So at time 0, you're 0 meters away from home, or you're at home. And then at time 10, you're somewhere there. Yeah. At time 10, you're not exactly 50 meters away from home, about 25. You're about 25. And as more time goes on, that happens. Then that happens, then that happens, then that happens, then that happens. Let me just draw this slightly more smoothly. Let's give it another try. Let's have something that looks like that. Something that looks like this. What could this possibly be? We're going to try to look at the gradient to figure it out, and also try to use our intuition to figure it out. Well, the gradient of this line, we can figure out the gradient of a curve either by differentiating. That's dy dx or d dx. Now this will be ds dt. Actually, the change in displacement out of the change in time. We can figure it out kind of by drawing tangents to this line. So if we come to this line and we just draw a tangent somewhere there, no, that won't really work out well for us. Let's see something else, a different color. Let's go back to green. So if we drew a tangent right there, like that, then we came here as well, sometime later, we also draw a tangent. We could figure out the gradient there. So the gradient here is actually lower than the gradient there, because the graph is not as steep here as it is here. The graph is more steep there, the graph is less steep there. And we have said that the gradient refers to the speed or to the velocity of the graph. So here where there's a higher gradient, that tells us that there should be a higher speed. And here where there's a lower gradient, that tells us that there should be a lower speed. So actually, this gives us a clue that if the gradient is changing, the gradient changes in a curve, the speed must be changing. So in the previous examples where we had straight lines, the gradient of a straight line doesn't change, at least as far as I know. A simple straight line, its gradient really just does not change. However, when you get a curve, the gradient is going to change. When the gradient changes, that means that the speed is going to change. But what's happening to the speed here specifically? It's increasing. Why is it increasing? Because the gradient is increasing as well. Could we have an example where the speed is reducing? Yeah, totally could. The speed is the gradient. So if we want to have a situation where the speed is reducing, we want the gradient to be reduced. So we want to start out with a high gradient, so something that looks quite steep. So at the start time 0, we want to have something that looks quite steep. Let's just undo that. Just have something that looks like that. There we go. A whole different color, but it should suffice. So let's look at if we can draw something that has a whole different gradient, where the gradient is reducing. So speed reducing means gradient must be reducing. So we must start out with a very high gradient, so something that looks super steep, and then as time goes on, the gradient reduces, it gets less and less steep, until finally it seems that the gradient is coming to a 0. Let's draw it in one go. If we do it in one go, it will come out more smooth. So there we go. So it will look something like that. So in this case, the gradient is actually reducing. You can see right there, we have that's the gradient. Well, right here, the gradient is actually there. You can see the gradient by drawing a tangent. You can see that the gradient here, right there, is lower than the gradient here. The gradient of the displacement graph is the speed, or it's the velocity. And that just tells us that the speed here is reducing. The object is coming to rest. This looks almost like a gradient of 0. It's not exactly straight, but if it was straight, that would be a gradient of 0. That would mean that basically time 40, there are the same displacement, still the same displacement, even after the time, still the same displacement. All these times the displacement is staying consistent, staying constant. So here they have a speed of 0, because as time passes on, they're not leaving the location that they were at. But I think I explained that before. And that's a bit deeper look into how displacement time graphs work, and we'd like to look at how to sketch them in the near future.